So in this video, what we are going to see is we'll be deriving the core group conductivity relation. For that, we will take three different both the schematic, that is this A, this is B, and this is C. Okay, we are having three different figures for describing or deriving our core group relations. So let us take this the first figure or the figure A. So we have sample here, and we have sample. The probe is kept over the sample, placed on the probe or sample, and the current is I is passing through this sample. Because of this current flow, right? So the spreading of this current will be something like this. It will be sphere, right? It is hemisphere. So the hemisphere, surface of the hemisphere will be 2 pi. Surface area of the hemisphere will be 2 pi r square. Right? Area of the hemisphere will be 2 pi r square. The surface area of the sphere will be 4 pi r square because it is half of that. Therefore, it is basically what you have 2 pi r square. Right? 2 pi r square. Let us assume some point P which is r distance away from the this contact point, right? So here this sample extends to infinity in this direction, the sample extends infinity in this direction, the sample extends infinity in this direction, right? That means the sample is sufficiently large in size, and this is the where the current flows in this sample. Now, what we will do, we will just take the electrical relation between the electric field, voltage, and then current density. Then we will write some relation, right? So let us take the electric field relation. Electric field is equal to J times rho. J times rho. So we know other relation. Electric field is equal to minus dV by dr. So you equate these two relations, and we will get something like is equal to minus, right, minus dV by dr, which is equal to J times rho. Here J is the current density, rho is the resistivity, V is the voltage, and E is the electric field. So now the current which is passing through this region, in this region, so will be the current density, that is the J. So current density J is equal to current by unit area. So therefore J is equal to, right, J is equal to current by area, which is equal to how much? J is equal to, right, J is equal to I by the area here it is 2 pi r square, right, 2 pi r square, that is the J. J is equal to I by 2 pi r square. Take this J value, substitute here. So what relation that we will get is the following. So that is minus dV by dr is equal to J into rho. So J value is this. So therefore minus I rho by 2 pi r square, right? 2 pi r square. So this is the relation that we'll get it. So we'll rearrange this and integrate to get the voltage value. That means what is the voltage that you get at this point P because of the current which is I, which is flowing in this direction, right, through the probe. The current is passing to the sample. We just want to estimate what is the voltage at this point because of this current flow. So therefore, we will just integrate this term, and then we will see, right? We will see what is the voltage that we get it. So therefore, what we have here is we just rearrange this equation. So dV is equal to, right, dV is equal to I, right? I can just write it d by dr, so which is equal to minus I times rho divided by 2 pi r square. Right? This is the relation that we have it here. So here it is plus, the plus is minus. So now we have this. So now we will integrate this to get the voltage. Therefore, if you integrate this, what I will get? Integrate it. So dV is equal to, now I will be taking this dr to the other side and integrate this. So the common term, the constant terms, I will separate it out. I will write it as minus I rho by 2 pi into 0 to r, because at this point I want what is the voltage. So the distance is R. The distance is R. From here, this is the point. It is 0. Here it is R. Therefore, 0 to R distance. I am just taking it. So therefore, 1 by R square into dr. I have to differentiate this to get the voltage. So I will be differentiating that. If I differentiate that, V is equal to, if I differentiate dV, that will be giving a V. So minus 8 times rho divided by 2 pi is in the denominator. If I differentiate this, what I will get is, minus 1 by R is equal to into 0 to R value. That is, if I differentiate this, integrate this, I will be getting this. So therefore, if I substitute this integral, the limits for this equation, so this minus and this minus will become plus. So therefore, I times rho divided by 2 pi into 1 by R. So this is the relation that we will get it, right? So now we will come to this the figure 2 or figure B. So now we will take two probes and see current is passing through this, and this is the point of interest where we want to calculate the voltage, and current is leaving in this way, right? Current is, assume the current is coming here and leaving this way. Therefore, this is the, so at this point we have to calculate the voltage relation. What we will do, so this is the voltage relation that we obtained. This is actually R, right? This is actually R. So here for this case, what we will do is the voltage will be is equal to I times rho divided by 2 pi into, into, so this is 1 by R, right? This is 1 by R minus I times rho divided by 2 pi into 1 by R square. Basically R is 1 by R 2, because this is, in this first probe the current is approaching this side. It is the second probe current is leaving. So this positive sign and then positive sign on this and negative sign on this simply means that here current is approaching the point P, and here the current is leaving the point P. That negative sign implies that. So therefore, what we can do is we can simply write it as I times rho divided by 2 pi into 1 by R 1 minus 1 by R2. So if I have a two probe, if I want to measure the the voltage at some point, I just have this relation. This can be extended for the fourth probe also.